Welcome to Dr. Acharya Academy. Today we will discuss about the chemistry class 11 taken from the CBSE syllabus, book number NCERT part 1 and unit number 1. Today's topic is Dalton's atomic theory. If you did not subscribe till now Dr. Acharya Academy, please subscribe it. Today's class number 007. Today's learning point is Dalton's atomic theory and its success and limitation. Atomic masses, molecular masses and formula mass. First, Dalton's atomic theory. In the year 1808, Dalton published a new system of chemical philosophy in which he proposed the following points. Number 1, matter consists of indivisible atoms. Number 2, all atoms of a given element have identical properties, including identical mass. And atoms of different elements differ in mass. Number 3, compounds are formed when atoms of different elements combine in a fixed ratio. This you have to remember, a fixed ratio he mentioned during the formation of the compounds by the atoms of different elements. Number 4, chemical reaction involve reorganization of atoms. These are neither created, that means these atoms neither created nor destroyed in a chemical reaction. So this is the 4 points what Dalton proposed in his famous Dalton's atomic theory. So with this theory, the laws of the chemical combination were explained nicely, but it was unable to explain the laws of gaseous volume, especially Gay-Lussac's law and Avogadro's law, which included the volumes, gaseous volumes. This Dalton's atomic theory unable to explain at that time. Now we'll come to the atomic mass. The atomic mass or the mass of the atom is actually very, very small because atoms are extremely small. Sophisticated technique nowadays, this mass spectrometry is used for determining the atomic masses accurately. Hydrogen being the lightest atoms we know, it is arbitrarily assigned a mass of 1 without any unit, and other elements are assigned masses relative to it. That means the atomic mass of other elements was based on the hydrogen atoms whose value, that means mass, is 1 without any unit. Now, the present system of atomic mass is based on the carbon-12 for the more accurate result, and this standard and has been adopted in the year 1961. So carbon-12 is one of the isotope of the carbon and can be represented as 12C, 12 superscript capital C. In this system, the 12C is assigned a mass of exactly 12 atomic mass unit, that means 12 MEU for the mass of atom of 12C isotope of carbon, and with this mass of 12 carbons, all other mass is assigned. One atomic unit is defined as a mass exactly equal to 1/12. This one you have to remember, 1/12 of the mass of one carbon 12 atom. So in this way, we can calculate when it is absolute in respect of gram, then 1 AMU is 1.66056 multiplied by 10 to the minus 24 gram. And mass of an atom of hydrogen is the 1.6736 multiplied by 10 to the minus 24 gram. Now the mass of hydrogen atom in respect of AMU, we can write the 1.0078 AMU and approximately 1.0080 AMU. Mass of the oxygen, that means the oxygen isotope 16O, its mass is the 15.995 AMU. Nowadays, this atomic mass unit AMU is replaced by the small u, which is known as the unified mass. Now we'll talk about the average atomic mass. Why you need the average atomic mass? Because when we use the atomic masses of elements in calculation, we actually use average atomic mass of elements. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, that means percent occurrence, the average mass, atomic mass of that element can be computed. Now I'll give one example for the carbon. Now the carbon has the 3 isotopes. In this table, you can see the 3 isotopes is the 12C, 13C and 14C. 12C relative abundance is 98.892 and its atomic mass is 12U or AMU, and 13C isotope relative abundance is 1.108 and its atomic mass is 13.00335 AMU or U. And for the isotope 14C, its relative abundance is the, in respect of percent, 2 multiplied by 10 to the power minus 10 and its atomic mass is 14.00317 AMU. Now we'll calculate the average atomic mass. So from this average data, above data, we can come out the calculation for the first isotope 12C, whose relative abundance is 98.892%. So if it go for fraction, it will be divided by the 100. Then the value will be the 0.98892 and multiplied by the 12U or AMU. Plus, now for the 13C. 13C's relative abundance in respect of fraction, because we have to convert from percent to fraction, then we have to divide by the 100 in every case. So in this case, the abundance is, absolute abundance is 0.01108 and it will be multiplied by the atomic mass 13.00335 AMU or U, whatever the unit is. Plus, for the 14C isotope, its relative abundance is 2 multiplied by 10 to the power minus 10. So absolute abundance will be 2 multiplied by 10 to the power minus 10 multiplied by 10 to the minus 2. That means ultimately 2 multiplied by 10 to the power minus 12. And it will be multiplied by the atomic mass 14.00317 AMU or U. And ultimately, if we go for multiplication and summation, then the value will be the 12.011 U. That means the average atomic mass of the carbon will be 12.011 AMU or U, whatever unit is. Similarly, for the other elements, we can calculate from the periodic table. If we know the isotopes, different isotopes of that particular element and its relative abundance and atomic mass, then the same way like carbon elements average atomic mass calculation, we can do for the other elements also. Now, molecular mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. Molecular mass is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. For example, molecular mass of methane, which contains 1 carbon atom and 4 hydrogen atoms. We have to remember here, when we'll talk about any elements, carbon atoms or hydrogen atoms, we always will count the average atomic mass. So in this case, the calculation, it has the 1 carbon, so its average atomic mass is whatever just now we calculated, it is 12.011 U, plus for the 4 hydrogen, 4 multiplied by average atomic mass of hydrogen 1.008 U. So ultimately the final calculation will be the 16.043 U or AMU. Similarly, for the molecular mass of water, in same way if you calculate, then the value will be the 18.02 U or AMU. I think that you understand very clearly the molecular mass also. Now, formula mass. Here you have seen one 3-dimensional structure. This is the structure of the packing of sodium ion and chloride ions in sodium chloride. In sodium chloride, you can find that 1 Na plus ion is surrounded by 6 Cl minus ions. If you see here, then you can identify this. This is very compact form, but you have to think that, and 1 Na plus ion always surrounded by the 6 Cl minus ion, and vice versa. That means for the Cl minus ion also, it is surrounded by the 6 numbers of Na plus ion. So the formula such as NaCl is used to calculate the formula mass instead of the molecular mass. In the solid state of sodium chloride does not exist as a single entity because it is not separate NaCl molecule. It is in compact form, packing. And in this case, we will consider the formula mass. We will not consider the molecular mass. When this type of packing of the ions will happen in a compound. So in this case, sodium chloride, the formula mass will be the atomic mass of sodium, 1 atomic mass, because 1 Na and 1 Cl, Na plus Cl minus. Only here you have to tell it is the formula mass not the molecular mass. So if you add the atomic mass of sodium and chlorine, that means 23.0 U plus 35.5 U, then ultimately final calculation will be 58.5 U for the formula mass of sodium chloride.